Hello, I'm Richard Patterson and welcome to another science video, and in this episode we're going to look at a very common practical which is in the English GCSE designated practical series, although it's common in specifications globally. It's the investigation of how the resistance of a wire changes with length. So the equipment you'll need is here. And we've got three IPC products. We've got a 24 volt DC power supply. It's also got an AC output, but we won't need to do that. It's a stabilized power supply, and this is going to provide our source of potential difference. It'll give a maximum of 3 amps. It's got a cutout on the control panel there, but we won't drive it further than about 1.5 amps in this practical. We're going to take measurements to calculate resistance using these IPC digital meters we've seen many times in other videos in our series. These are angled so that the students can get a view of the output clearly, and it's got these side connections which again allow for easy manipulation and setting up on the bench. In addition, we need to build using a meter rule, a length of resistance wire 1 meter long, and we're using 22 standard wire gauge nickel chrome wire here. That's an alloy of nickel and chrome to provide a good change observable by the students as we alter the length. We've secured the length of the wire using 2 Hoffman clips because we need to think about the actual wire length itself and where it starts and when it stops. In some versions of this, we use a crocodile clip to make a connection to the wire. We've used this piece of equipment that was used in A-level, in the Wheatstone Bridge, in the potentiometer experiment, and we call this a jockey. It's got a sharp metal edge to it, which means that when we place it on the wire, we can read the distance, the length of wire in circuit, a little better than using this crocodile clip. So I'll connect up the circuit and then we'll take some measurements. We'll begin with the negative side by connecting from the power supply using this crocodile clip, and we'll put that on the Hoffman clip there. Then we'll work on the positive side from the power supply into the positive side of the ammeter, from the negative side of the ammeter through the jockey, like so, and by touching that on the wire there, that will complete the circuit. So I'll just do a little test of that. Switch on the power supply, switch on my ammeter, and I only really want to make contact with the wire momentarily and take the readings, otherwise there could be a chance of the current heating the wire up, and that's our control variable of constant temperature jeopardized. So there we are, we've got around 70 centimeters of wire in place, and we're drawing about 0.347 amps. So that's working okay. I now need to put the voltmeter in parallel. So if I connect one side of the voltmeter to the negative side of the power supply, switch it on, and connect the other side of the voltmeter to that connection on the ammeter, connecting to the wire there. Again, there's our 0.32 amps with about, in this case, 77 centimeters, and we've got a voltage across there of about 0.8 volts. Change the connection, record it, and then gradually work down the wire, reducing the length of resistance in the circuit. Now at some point, if this current exceeds 2 amps, then the ammeter is going to go into the overload stage. So we don't really want too small a resistance of wire there, because too small a resistance wire will result in a bigger current. So I'm just going to go down the wire there, recording the length and the corresponding pair of potential difference and current, and that's my experiment completed. We now need to draw up a results table. So begin with a column with the title length of wire in centimetres. This will be the independent variable. Second and third columns for our pairs of readings of potential difference in volts and current in amps. Finally, we have our dependent variable, the resistance in ohms of the wire for a particular length, and we'll calculate that by dividing the potential difference by the current. So we can now complete our graph. Begin by plotting the points, the length of the wire along the x-axis, resistance along the y-axis. Make sure you label your axes resistance in ohms and length of wire in centimetres, and give it this title, resistance versus length of wire. From our results, we do get a straight line relationship. We've drawn our line of best fit through the set of points, and from this we basically can observe that as the length of the wire increases, so does the resistance in ohms. It's important to understand the variables in this experiment. The independent variable will be the length of the wire. The dependent variable will be the resistance, but note that to calculate this we first need to measure pairs of potential difference and current for each length of wire, and then we'll calculate the dependent variable by dividing potential difference by current. We've got two control variables here. The first is the cross-sectional area, the thickness of the wire, and we need to ensure it's the same diameter for all lengths. And secondly, the temperature, which we keep constant by using a low current, switching the circuit off between readings. Well, thank you for watching this episode. As ever, you'll find details of these IPC products on the website by following this QR code. And if you'd like detailed teaching notes, the IOP Spark episode number 124 tells you all about the variation of resistance with dimensions such as length and cross-sectional area.